Right, cool. Welcome back. So we're going to continue on the Ethereum as the world computer. So as I said, we now sort of understand the consensus, blockchain, how blockchain first achieved the very first version of self-regulating currency. Let's see what's Ethereum, how Ethereum is different. Let's start with the limitation of Bitcoin. Okay, I didn't explain UTXO, but UTXO is an unspent transactions. So let me just use this figure. So Bitcoin as a state transition system, you can think of it as this way. In one state, at a specific moment, in the world of Bitcoin, the entire Bitcoin state can be defined as a set of all the unspent transactions. They are the transactions on the Bitcoin, on the blockchain. So they are up on the blockchain, confirmed, but they have never been spent, meaning that money is there, Bitcoin coin is there, but no one has spent it out from that account. So if you collect all the set of transactions that are unspent yet, then that becomes a world state. In Bitcoin, those transactions are the money, coins are or the entire defines a set of states of the Bitcoin world. And when you are making any transaction to this, let's say, try to spend the money in the UTXO2, meaning that you are actually finally uses that money, coin. Then you're removing this UTXO2, but now you're creating another unspent transaction, because by definition, you are making a transaction which is unspent yet because you just created. So again, the world state of Bitcoin is defined as a set of unspent transactions. Clear? If we formalize it, the Bitcoin rules is simply a state and times the input, all possible set of inputs from all set of world state to an updated world state. So that is the Bitcoin. And Bitcoin is useful for moving around monies, and that is actually it. But you cannot really do more than that. So limitation here, one limitation is that it is difficult to maintain the state in multi-state contracts. Like, in addition to sending one money to others, if you want to do more than that, it is hard. And it is hard to enforce global rules on the assets in Bitcoin. So for example, let's take an example. Like you want to, let's say, have some rate limiting. Like, you have a wallet manages 100 UTXOs, okay? There's wallet has 100 transactions that are unspent yet, okay? Those 100 coins, in other words. You may want to have this desired policy. You can only transfer 2 BTC per day out of my wallet. You have a set of 100 UTXOs, but in total, you can only transfer 2 Bitcoin per day. How can you really enforce it? How can you do that? You cannot do that in Bitcoin. So you heard about the Silicon Valley Bank last week. It's just last week. The bank run was possible because lots of people actually withdraw money using their cell phones, almost at the same time. So rate limiting didn't really work. In Bitcoin, can you have some rate limiting like that to prevent bank run? You cannot do that because it will just work. So Ethereum is trying to do better than Bitcoin in the sense that it can write a contract and in a Turing complete language and you can write code, and you can implement any interesting like rate limiting or any applications in general, and then you can enforce it. So that is the thing. So that enables DeFi. You can create exchanges and lending, stable coins and derivatives. So as long as you can write a code and write a uh, uh, products, then it works. Insurance, you can write it. You can run a decentralized organizations and NFTs and so on and so on. So how is it different from Bitcoin? Ethereum as a state transition system, it's a much richer, it has much richer state transition functions. So one transaction executes an entire program, not just a money moving around from this account to that account. It actually executes an entire program. So Ethereum's world state is much richer than Bitcoin. And how is it different? One biggest difference is that you can run a program on a blockchain. So now we are actually getting closer to what you guys will be creating for your Web3, because now we'll be talking about a program that runs on a blockchain, and that program will likely be one of your Web3 applications. So first you create a decentralized app. It's just anyway a program code, okay? And along with the initial state of that program code, it goes on top of blockchain. So far in our discussion of Bitcoin, everything that goes onto the blockchains are transactions, and that's it. That was it. No other things. I mean, you can add something, some fields in those transactions for a little bit of computation, but it's very limited computation. With those limited computation, you can actually write some interesting things, but very limited. But here, what we're talking about here is the program code. It's written in different languages. Solidity is the one popular one, and which you will learn 2 weeks from now, and that is uploaded to blockchain. And whenever there is another transaction that invoke that program code, then the states of the program code changes from state 0 to state 1, and it is recorded onto the blockchain, and it goes on, which means that the program that you upload to the blockchain is being executed as time goes by, and then it is visible to anyone who has an access to the blockchain. And somebody has to execute this program. And what is that somebody? Is EVM, compute layer or execution chain. In the 2.0, Ethereum 2.0, we do have consensus layer, but that's another story that I'm going to be talking about towards the end of today's lecture. So in the Ethereum system, the consensus itself for the proof of work, old version of Ethereum, because Ethereum used to run on proof of work, it was similar to Bitcoin, with some differences, including that one block is created every 12 seconds, as we have discussed. It is much shorter than Bitcoin, and it because of this, you need to, attackers requires little less than 50% to subvert this Ethereum, but that's the price that you need to pay for faster block generation time and about 100 transactions per block. And block proposers receive transaction fees for a block. So I actually didn't mention about the transaction fees for Bitcoin, but we'll get to that point for Ethereum. So consensus layer itself is not that very different, at least for the proof of work version of Ethereum from Bitcoin. What's different is that in the blockchain and the Ethereum, you can write a code and the code will be executed by EVM. So every miner in Ethereum runs the EVM, and it actually executes the program. And there are two types of accounts. The owned account are just the money, just the wallets that keeps some amount of coins like ETH in Ethereum, and the contracts are the accounts controlled by the code, and code sets at the account creation time, and it does not change. So why the code that you write for your Web3 does not change? Here's the answer. In the Ethereum, you write a code and then upload it to the blockchain, and it should be there, and it is confirmed in several new blocks. After several new blocks are attached to that, and then it is confirmed, then the code is there forever, will be there forever. You cannot really change that. And for your application, you can actually have a storage, and I think a lot more details will be available when we discuss Solidity later. But there's a limited number of storage, and account storage root is computed using Merkle-Patricia tree hash. And because a full Merkle tree hash can be quite expensive, so we use this Merkle-Patricia tree hash. And transactions that you send in Ethereum is quite similar to Bitcoin's transactions, except that it has Ethereum addresses, and it has also, of course, has a signature just to verify that verify the authenticity of this signature and the integrity of it, and the value that the amount of ether that you are sending for in your transactions, and fees, because with some fees you can actually incentivize the miner. And also fees are much more important and nuanced than Bitcoin, because now you are asking the miners to execute your code, and they're burning their CPU powers and memory as well, so you need to pay for it. And if you think about it, there are not only one miner, there are many other miners. So if you upload your code there, then all the miners will be executing your code, so you need to pay a lot actually. So that is an interesting topic. So and then for solving the proof of work, then in the same way that Bitcoin miners solve the proof of work puzzle, you need to find a nonce to solve the puzzle. So transactions can be sent from the owned account to another owned account, in which it means that you are actually transferring ETH between users, just like you're sending Bitcoin to others. If you're sending a transaction from the owned account to a contract, it means that you are calling the contract with ETH and the data. So for example, if you see this, there are some examples of the Ethereum block, which includes some of the transactions from one account to another, and some of them are going to the code smart contracts. So also one thing is that you can also create transactions and then send it by a contract, so that code can actually send funds to other users, in which case your contract is sending the transaction to owned. In the case of DeFi applications, you send some money to the DeFi lending service, and then you get some interest from the smart contract. Then money goes back to your owned account. Also, you can a contract can send a transaction to other contract, which means that from the programming language's perspective, one program calls another program and sends funds as well. So it really opens up lots of opportunities for developers to write not only a little bit more complicated money applications, but basically lots of different applications. And you can also write a transaction that actually triggers your contract to send another contract, and you can compose the contracts in this way. So this is another reason that Web3 is composable, in the sense that there are many existing services for Web3, and you cannot really, you don't have to implement all the layers in Web3, but just to grab some others Web3 applications and then use it. Because if they are in this Ethereum, then Ethereum ecosystem, you can actually just call them. And this is open system. You can execute others' code without any problem. So that is really the what Ethereum really opened a gate for us. That's the main difference between the Ethereum and Bitcoin. So let's look at this example. On the left hand side, this is the world state before this transaction, and on the right hand side, this is the world state after the transaction. So in other words, updated transaction. There are 4 accounts, and where we are focusing on the top 2 accounts. First one is the owned account, which means that this is someone's money, okay? And the second one is a contract. And this transaction saying that it's from this address. This address corresponds to the first account. So meaning that the owner of the first account wants to send something to whom? The address of the second contract, okay? So meaning that this address owner of this first account wants to run this contract, the second one, okay? By sending 2 things, value, 10 ETH, 10 Ether, right? So after that, the account now has 10 ETH less than before, right? 10, 14 ETH. And the data field has 2 fields, 2 and Charlie. And this data will be processed based on what is written in the contract. So if you look at the contract itself, it sees that the TX data 0, and that is the index of the contract storage, which is written below, and 2 means the location here. If this is if this is 0, then you need to update it with the user provided string, which is Charlie. So after that, this contract has 10 ETH more than before, and the storage and internal state of this contract has been updated. Okay, so effectively, you are who owns this first account just called this contract and executed it by paying for it, and then you change something. And that's why Ethereum becomes the world computer, because it is available, this code is available for everyone. I mean, if you can pass this very first access control, if there's any access control in this smart contract, then you can execute this. So it's a world computer. Literally, it's a world computer, because there are lots of miners are executing those code. Producing a block there's nothing much different from Ethereum's point of view compared to Bitcoin. So I'm just gonna skip it quickly. So look at this, it looks similar to Bitcoin. The only difference would be that updated world states are actually accounts and those states of the smart contracts, and it has log messages as well. But overall, it is similar to Bitcoin, because the miners has to compute and execute a node. Basically, it's, again, it's not just sending money around, but you are running a program. So the amount of memory to run a node is going larger and larger. It now is more than 1 terabyte. So Ethereum total blockchain size, if you archive everything, then it's 12 terabyte. So it's getting more expensive to run an Ethereum node. In my own lab, we are running a number of Ethereum nodes for research purposes, for measurement, and all sorts of purposes, and it costs a lot. It's so expensive these days. I actually was going to talk about this contract as an example, but I am going to safely skip this because we will, get to this point very soon when you learn Solidity very soon. One thing that I want to mention is that this EVM mechanics has to execute those code written in Solidity, maybe, and you need to run it. Then it costs money. So so it costs money, and for that there's a cost involved in it, and that is the gas. So gas is obviously named after gasoline that runs cars. So you need some fuel to let the miners run the code, and gas is the unit. So gas is the transaction fees that you put when you are sending a transaction. So for example, when you are sending a transaction to run a certain smart contract or certain code, then you set the maximum gas that you are willing to spend. And if after running the contract, then as the miners running the contract, they calculate the amount of gas they have to use for the calculation of it. For each operation that they have to run in this EVM machine, there's a price tag for each operations. So transaction senders can estimate, the gas amount and set the number. And this is useful because otherwise, people will send a bunch of transactions to clog this entire system, and then the entire system will be too busy to handle so many transactions and executing those code, and it becomes unavailable. So gas has to be set, and the price of gas is determined based on some computations and some competitions, which I'm not going to really go into details. But the gas price actually, you see the gas price actually experience some spikes whenever more and more people wants to run things in Ethereum. It becomes more expensive. So more and more code in Ethereum network, higher the cost. So gas price in Gwei is a much smaller unit of Ether, and it changes over time. Sometimes it spikes. So total gas usage is for I think for total gas usages increases, which means that more transactions are sent to the miners, and the Ethereum miners actually has a maximum amount of gas that they can actually use for the execution of this entire block, so that they can have some limit. Otherwise, the block size, either the block size or block generation time can go forever, and then it will clog up the network itself. So there's a safety boundary there. and the price actually will regulate the whole thing. You know, if it's too expensive, people will defer the transaction, and then that actually slows down the Ethereum network. In the last part of this Ethereum section, I want to talk about something about proof of stake. You will hear a lot more about smart contracts later parts of this semester. But proof of stake, maybe this will be the last time. So let's spend a little bit more time on proof of stake than smart contracts. So if you have heard about this, if you've been following Ethereum in the last few months, then you may have heard about the term the merge. So they actually call it the merge because it is really the big event, and it got a lot of attention and a lot of worries and concerns, but it went okay. So in this timeline, like I said, Ethereum initially it was a proof of work system, just like Bitcoin. And miners burning their CPUs and burning electricity basically, and to find the solution to the hash puzzle, and then any winner will be the next leader who determines the block, which we all agree, we all understand now, okay? But at some point in some time 2020, they started out this beacon chain, the blue one, okay, blue one beacon chain, and try out this notion of proof of stake. And proof of stake is actually has been discussed a lot, much longer than older than this actually. In 2014 or 15, people were talking about it, and Ethereum started to test this out. And now 2022, it's got merged, meaning that proof of work stopped. No more proof of work, only proof of stake. And from the Bitcoin to proof of stake, let's see what are the differences. And there are some differences other than electricity. I mean, electricity is the one that makes proof of stake much more appealing than proof of work, and that's very clear. There's more than that, actually. So since the Byzantine general problems, basically the agreement problems between untrusted parties, Bitcoin kind of solved this using allowing open participation while achieving dynamic availability and Sybil resistance. That's a really cool idea. And it also, create this very cool idea of block rewards as a carrot to just it's an incentive to for the hard work that the miners has to put in. That's good. Proof of work Ethereum also followed it. So basically, from the consensus point of view, proof of work Ethereum and Bitcoin, there's not much difference, other than some of the parameters, like the block generation times and then block sizes and blah blah blah. Not much difference. Proof of stake Ethereum is different. Proof of stake Ethereum also provides open participation, which is good, which is very important for this large ecosystem, because anyone can validate it. So you don't have to trust a small number of people there. It provides dynamic availability, just the same way Bitcoin does, and Sybil resistance as well, which is good. It also provides block rewards, like carrot. It also provides finality and accountable safety. So these are the things that are added to the proof of stake Ethereum. So we'll see what are those and why they are really cool, and is there any concerns about it? Okay, so let's see. For the purpose of this semester, this course, we want to define the proof of stake in an informal way with some few highlighting, statements. So in a proof of stake protocol, nodes lock up their coins. So if you want to be the participating nodes, especially the nodes that is participating to the consensus, you need to actually pay upfront. But we don't say pay, but lock up, stake their coins in the protocol to become eligible to participate in consensus. We need to pay for it. You can get it back, but you need to put some money on the table to play this game. Okay, and the more coins staked by a node, more money on the table, then you have higher probability that the node is elected as a leader, right? It's a leader selection operation. It's the same as proof of work, but in a slightly different manner. And the larger the weight of the and if you place more money on the table, then you can have more votes. So what is a vote? The notion of vote didn't exist in Bitcoin and proof of work Ethereum. It actually existed implicitly, but now votes exist explicitly here. Let me explain in the next few slides. If the node is caught doing an adversarial action, it's like doing something weird, doing something that they shouldn't do explicitly, then they can be punished. How they get punished? They put some money on the table, and some money on the table, or all of their money on the table, are taken away, just burned. So it's gone. So this is called slashing, or it's a punishment, but slashing is a extreme form of punishment in this case. This makes sense because you have to first put some money on the table. Protocol itself will, take it away if you do something bad. So therefore, in a proof of stake protocol, nodes can be held accountable for their actions. If you do something wrong, you are responsible for your action, and there will be consequences. There is consequences. In Bitcoin, there's no such thing. In Bitcoin, if you remember the 51% attack, right? Let me just quickly go back to that. Where is it? 51% attack, right? Attackers are secretly generating blocks without sharing with others and creating a longer chain. I mean, doing some weird things and really malicious things, but there's no consequences of this. But I mean, let's say you try this, but you failed, but no consequences. But in Ethereum, proof of stake Ethereum, there exist consequences. Let's use this cool animation made by I think it's a PhD students at Stanford, and to understand proof of stake. So the protocol runs at each epoch. In each epoch, you will see a block, okay? And in this case, so this guy proposes a new block, and this guy, it's this guy's turn. We take turns based on the number of coins that you are staking on the table. You put on the table, okay? More money, you have a better chance to become a leader. So anyway, it proposes a block. Then people vote on this block, explicitly send this voting messages called attestation, and now this block includes this attestation with, in this case, all the miners, all the validators in this case, in Ethereum, validators, attestation or votes will be selected as the block. And then let's say there are two blocks, tries to extend this already finalized block. Then let's say 6 of them, 6 validators vote for this block. So it looks like, 6 out of 9 votes for this set of transaction or block. Now looks like this will be chosen as the main block. So which means that TX transaction set 5 will be ignored. But this 3 will, vouch for this block. But at the same time, 3 malicious guys making double votes. It's called equivocation attack. Basically, they are making double votes, which they shouldn't do. They are strictly prevented to do so, but they did it. Then, if the protocol sees this, everyone who's running this protocol can actually see that there's a problem. 3 validators are throwing double votes for the 2 blocks at the same height, which shouldn't really happen. And all the votes are signed by all the senders. So this can be trivially detected. And when this happens, protocol violators who has done something wrong, their coins are removed from the stake, which means that they just lost money. So this is a simple, illustration that shows that proof of stake not only works well and guarantees the safety of the system, but also it held the violators accountable for their own actions. So this is called the accountable safety. It provides safety, but it is better than that. So in the protocol with resilience of n over 3, typically in the system, for Bitcoin, you can actually think of it as a 51% from our own context. So we can say the protocol is secure, safe, and live if there are less than a certain number of adversary nodes, which is something we are aware of now. In the protocol with accountable safety resilience, like in this case, the protocol is secure if there is less than a certain number of adversarial nodes, which is the same as before. In addition to that, if there's ever a safety violation, as we have seen in the previous example, all the observers of the protocol can provably identify and catch those adversary nodes as the protocol violators, and they got punished. So no honest node is ever identified. If they send 1 vote for each height, then there will be no false accusations. So this is actually a very cool property. And this is all possible because this whole system is based on the proof of stake, meaning that all the active participants, like validators, if you want to participate in the consensus, then you need to put some money on the table. That's really it. That's really what enables this kind of penalty and slashing possible, and it makes safety resilience accountable, or accountable safety. And so this is another illustration. If an attacker has more portion than a certain portion, then now the attacker system has no liveness or safeties, but with the accountable safety here, if it's violated, then you can catch and punish the adversarial nodes, which was not possible in the Bitcoin-like system, proof of work system. Accountable safety is a pretty good property, right? That we see in Ethereum 2.0 or Ethereum after the merge. Another interesting and important property that people really like about it is the finality of it. So most systems, so Bitcoin does not really have a finality, in the sense that, as I said before, it has confirmation, or it has probabilistic finality, with like 99.99% final, with small percentage probability, there's a chance that your transaction deep in the network, I mean the Bitcoin blockchain, can be actually reverted. With the finality, it won't happen. So what we want is to finalize transactions. So let me. So this is what we call the holy grail of internet scale consensus, because it has been very difficult. So we want Sybil resistance using proof of work or proof of stake. We also want dynamic availability, so that when things go wrong, like worldwide catastrophes, still the system should go on. And
Professor
we
Ka,
also want,
Professor,
yes,
sorry, there is some noise from your part.
not really.
Yeah, it is
Sorry.
a little bit.
Really, I'm using my Mac microphone, and actually I'm in my office, so it's very quiet here. So what kind of noise are you hearing?
Okay, I think it is resolved.
Oh, it's now okay. It's okay.
Yeah, okay.
Okay. 네. 또 이상하면 얘기해 주세요.
Yeah.
Okay. So finality. So we want finality and accountability. So that there cannot be any safety violation during any asynchrony. So when there's any synchrony problem, network temporary partitioning of the network, we still want to have this finality property in the network, which is very hard. So achieving all this has been discussed, but known to be very difficult, because of the simple reason. In this example, let's see that there are 6 replicas or miners or validators, okay? And there's a client Alice here. Let's assume that there exists certain protocol that has both dynamic availability and finality, and see what happens. So let's say the 3 replicas on the right hand side becomes unavailable. Then if we have a dynamic availability, system must go on. I mean, this blockchain still should grow, because the remaining parties should be able to somehow make an agreement, and then should be able to provide correct logs of those, agreement, and then provide a log to the client. Okay, so this makes sense. Like, they don't know what others saying because they don't hear anything, but this is what it is, and then move on. It's a dynamic availability. Finality, is it really possible? Let's say the network is split for some time, and then if this temporary partitioning happens, then the left hand side on the right hand side, they may arrive at the different states. And why is it? Because they cannot talk to each other for temporarily, and then they're it's a safety violation, because they arrive at a different agreement. Okay, so you cannot really achieve the safety, and therefore there's no finality. So this is actually a hard problem, and Ethereum's approach, is to have a nested chain to achieve both. So I have a good illustration of this. So when there are a number of validators here, and they're trying to agree on the set of transactions through proposing a block. So in this case, A proposes a block, and the next guy proposes a block. So it works in this way, and it is available chain, because they do their best for with the available nodes. And in this case, A proposes block 5 and checkpointing it. This checkpointing protocol uses another vote to make a consensus that up until this block 5 is finalized. And then this becomes a finalized, meaning that it is locked. So no matter what, you cannot really revert anything in these locked blocks. It's finalized. It's not only just probabilistically confirmed, it's finalized. So it's finalized. And after that, some of the nodes may go offline for some reason. And does the network grow? If we really want to, have this, so since the network works with the proof of stake, and as long as some number of nodes with enough stake still alive, then they can become the leader, and then they can propose a block, as you can see here. And then at some point, this gives you a dynamic availability, because you always extend the last checkpoint. For the checkpoint, you need a majority quorum to actually have an agreement that up until this point is really all finalized. And after some of the nodes back online, then they see what's happening there, and then some of that propose the block that they have never actually seen when they are made, and then actually they can go through this voting process to finalize those blocks after all. So in the Ethereum proof of stake protocol, there exists explicit voting process, and for the block generation, and also for the checkpointing protocol. So these two sets of protocol actually work together. That makes Ethereum, we can call it a nested chain, and then that way you can achieve finality and dynamic availability for the temporary network instabilities. So proof of work Ethereum now, in their own terminology, for the available chain, there's a protocol called LMD Ghost, which provides dynamic availability, which is quite similar to Bitcoin's heaviest chain link, but with the difference with explicit voting. For the finalization, they use Casper FFG friendly finality gadget for checkpointing protocols. So with these, the finalized chain of proof of stake Ethereum provides accountable safety. Why accountable safety? Because if there's any violators, then you can actually make them accountable for that. So I actually didn't keep the time, but this is almost the last slide. So then Ethereum is too cool, really cool. It provides more than what Bitcoin can provide, and also it can provide us a world computer. We can run any arbitrary code there. Is this Ethereum the end game? The answer is probably no. It is a really cool thing, but it's not sufficient yet, because the throughput and latency, it's still a problem. Lots of transactions per unit time, how many transactions we can support for Ethereum, and the latency, time frame for confirming a transaction, it still takes some time. So it's not really 1 second finalization yet. So then what do we need? So next week, we're going to talk about the next topic, blockchain advanced topics like L1, L2. So far, we've been all talking about L1, layer one main chain, and there are many L2 candidates, and that also sometimes all includes zero knowledge proof and sharding as well for increasing the throughputs. So I'm going to give you another short ish lecture about that advanced blockchain technology, and then Dr. Sam Saw from Clayton Foundation will give us a lecture about how difficult it is to build a blockchain platform in practice. So far I've been talking about many different things, but maybe you may have this feeling that, oh, blockchain is so cool. I mean, we can easily write it, but writing a real blockchain platform is much more complicated than that. And Sam will be talking about that next week. Okay, with that is my really the last slide. It's been a very long talk, but if you have any question, please let me know. You can use the chat or yeah, you can use your microphone. Otherwise, I guess that's it. So Jason, do you want to say something before we wrap up?
Nothing. It's a great talk.
Okay. Then we can say goodbye now. See you, right? I think there was a question. Okay. If the coins removed from the stacked coins, are they deleted permanently? Yes, they burn it. So as a penalty, so you place money on the table and some are burned. So that's a penalty. If Alice account, another question from Haley, Hale, if Alice account has not enough ETH when the transaction is tried, what happens? How can Ethereum meet prerequisites of various smart contracts it holds an amount of? So, okay, so if let's say you send a transaction with gas, which is not enough to finish it, then miners will try to run your, process your transaction, and soon they will realize that the gas is not enough. Then the amount of gas that was used for that operation but not finished will be used, will not be returned to you, because you are actually you've been already using someone else computing resources. This is not returned to you. Not also balance. Balance you go back to it goes back, right? Because it's not processed, if I'm not mistaken. Yes, balance goes back, but gas is not returned. And that's important because otherwise people will send a bunch of transactions with slightly, insufficient gas for denial of service, which shouldn't happen. Yeah. Let me know if I'm not correct, because some of you guys know better than me when it comes to Ethereum. Okay, another question. It means that transaction is not executed even every conditions are met. If you don't have enough gas, then transaction is not it's not correctly executed. It's not executed. So did I understand your question correctly? So one transaction and then execution of the transaction. So this is an input. One transaction is an input to a program, right? And then based on this input, you are executing the program. and you actually don't know when the program ends. This is classic halting problem. You execute the program as long as you have any leftover gas, right? Execute one operation, your gas is decreased and it becomes 0. You still couldn't finish, end the cycle or whatever this program wants you to do. Then it is reverted back. So it didn't happen. The gas is gone. The transaction didn't happen. If you finish the operation, execution of the code, while you still have any 0 or positive gas, then it is done. Then the blockchain state has changed from previous state to the next state, because everything that you have executed now should be updated and reflected back to the blockchain. Does that make sense? Oh, another question. They should execute always when the condition is met. Yes. So yeah, when the condition is met. Yeah. I think that the condition may include many different things, but gas and yeah, I think the details of how you actually execute the smart contract, that's that's something we're gonna be talking about a lot when we actually go to smart contract lessons. Any other questions? Any other follow questions? Any other doubts? Any other? Okay, cool. It runs. Sangu just said it runs only when any user triggers the smart contract, when it meets a proper condition in the contract, and when the user contains enough gas fees. Yes, that's what I agree. Yeah.
Actually, we will have a Solidity and Smart Contract lecture from Ethereum Foundation. So you can learn a lot of things from him, and you can ask many things about smart contract and how to pay for gas or other Ethereum issues.
Right, exactly. So I should have said it up front. I'm not an expert in smart contracts. So I've studied and learned and researched the blockchain from the bottom of the layer up until consensus, and I've just very basic experience in smart contracts. So that's what I actually am trying to learn from this Web3 lecture series. I also very look forward to lectures about smart contract and Web3 cool applications as well. So yeah, you will have a bunch of opportunities to, we will have a bunch of opportunities to talk about these issues. Any other questions? Let's wait 10 more seconds and if there's no questions, let's wrap up. 오늘도 잘 공유해 주시나요? Yes, yeah, it's been recorded, so yeah, it will be posted somewhere. Okay, yeah, thank you for coming to the lecture, and I will see you next time.
See you next time.
Okay,
Thank you.
bye bye. Yeah,
Bye.
thank you.
교수님
Bye.
수고하셨습니다.
수고하셨습니다.
고맙습니다.
네.